So we're going to finish thermodynamics today and start in with talking about oscillations. This here, by the way, is the Otto cycle. I was talking to some students about the homework problem that we took out, and I talked about these strokes that we just don't draw because they don't have a net effect. If you look at those strokes going from position 6, okay, I got to erase it so we can see it. From position 6 to 1 to 2, how much work is done going from 6 to 1 and from 1 to 2? The net work for those two is 0 because the area enclosed, it is a complete cycle going from 6 to 1 back to 2, and the area enclosed is 0. So there's no work in the intake and exhaust strokes, hence we usually don't even consider them. So when on that homework problem, for those who did it just, for the experience, it only had the 2, 3, 4, 5, 6. It didn't have the 1 position because that's not contributing. The combustion process is burning the gas. That's where I tend to think of it starting. And then you have the very rapid expansion. Because it's so rapid, it's adiabatic. There's not time for the heat to flow. And then it says heat rejection here. Honestly, I'm not sure what heat rejection is supposed to mean, so I'm just going to move on. You might remember people who I was going over this in the class or in my office. I did likewise. Then you push the exhaust out. You bring in fresh air, you compress it. And so you have the compression stroke there, which once again, the compression is quick, and thus we consider adiabatic because there's not time for significant heat to flow. So that's the Otto cycle. That's what's going in your car. That's idealized. The reality is a little bit different, but it's reasonable. Now we're going to shift from a heat engine to a heat pump. This was on the test, but as a review, what was the purpose, or what is the purpose of a heat engine? Convert thermal energy into mechanical energy. And the second law of thermodynamics demands that even in an ideal situation, for instance, the Carnot engine is the ideal situation, even if you could really make a Carnot engine, the efficiency can't be 100%. You're always going to have some exhausted heat. You can never have 100% transfer of heat into work. That was another test question. Now, a heat pump and a refrigerator are the same thing. If the goal is to heat, we usually call it a heat pump. If the goal is to cool, we call it a refrigerator or an air conditioner. But they are the same thing. And the purpose of a heat pump or a refrigerator is to use mechanical energy to move heat. It's actually exactly the opposite of a heat engine. A heat engine uses heat to produce mechanical energy. The heat pump uses mechanical energy to move heat. And so the schematic diagram for a heat pump is shown here. And you should note that's exactly the same as the schematic diagram for a heat engine, except for one very significant difference. What's that one significant difference?
Isn't there two? Like the work should be going, or in a heat engine, the work is going out, but it looks like the work is going in. And then the cold usually is going out. But in this case, it's going in.
All of the directions are reversed. All three of them are reversed. So that's what I meant by the one difference. The directions are reversed. So what that means is, basically, what we have learned about a heat engine, we have the same rules for a heat pump. That is, for a complete cycle, we're going to have the change in internal energy is 0. Otherwise, you either melt it or reach less than absolute 0. Which means that if you balance, using the first law of thermodynamics, energy can't be created or destroyed. And if you're not increasing the energy of the engine or decreasing it, then the energy in must equal the energy out. So that means in is work plus Q cold is equal to out, which is Q hot. That's the same relation we had for a heat engine. The difference, of course, is what you're trying to get out. Let's say you're using this for a heater. If you're using it for a heater, what is the important thing you want out of your heat pump? Which heat is it, QC or QH? It's QH. That's your output. And what's your input? Your input is the work. You're putting work in to move heat, and you care about what the QH is, right? I ask you this question not for people to answer wrong, but for people to think about the reasoning of why we define the input as the work. Because obviously the QC is going in, but the work is what we're putting in. The QC is part of what's being pumped. And so the input is the work, the output is the QH. So for a heater, the coefficient of performance is equal to what we want out, QH, divided by what we put in, the work. Now, this is the coefficient of performance. When we did the heat engine, it was called the efficiency. It was called the efficiency because we were converting energy from one type to another. Here it's called the coefficient of performance because rather than converting energy, we're transporting energy. And so the performance is how much did we transport of the kind we wanted divided by how much we had to put in the work. There's also another significant difference. Remember, the efficiency was always less than 100%. If you take this, you'll see right away, wait, the efficiency for a heat engine was the work out divided by the QH. So the coefficient of performance for the same system just run backward is the efficiency of the heat engine. But since the efficiency of the heat engine was always less than 1, what does that tell you about the coefficient of performance? It always has to be 1 over something that's less than 1, which means it's always greater than 1. Now, that's a really good thing to note right off the bat. You can go to the store and you can purchase a little space heater. It has like an electric filament. You put electricity through it, it gets hot and it heats the room. That's not a heat pump. That is directly converting the mechanical energy, in this case electrical energy, which we consider mechanical because we can use it, into thermal energy. Its efficiency is very close to 1. Surprisingly enough, if you have a light bulb, like when you're a kid, you might have had an easy bake oven that bakes using a light bulb. You can actually bake cookies with your easy bake oven with using a light bulb. As a heater, a standard incandescent light bulb is about 95% efficient. Of course, what do you use a light bulb for? For lighting. If it's 95% efficient at heating, how efficient is it at lighting? Yeah, it's close to 5% efficient for lighting. So incandescent light bulbs are very low efficiency. If you go to something like a fluorescent light bulb, the fluorescent light bulbs are somewhere around 30% efficient. And you're like, oh, that's only 1/3 of the energy. You're still throwing away 2/3. But compared to the incandescent, that's 6 times better. And so that's why there's been the push to move to compact fluorescent light bulbs in your home, and then from compact fluorescents to what's the current rage? LEDs. LEDs are just about the same efficiency as compact fluorescents, but they have some other real distinct advantages. Not the least of which is the compact fluorescents, despite their claims of lifetime working, mine have always burned out in less than a year. Compact fluorescents have been highly unreliable to me. Okay, but what was the point of this? You can go buy that little space heater, and it's going to be less than 100% efficient in converting the work into energy. Your worst possible heat pump is going to have a coefficient of performance that's greater than 1. It's going to be more efficient. So heating your house with a heat pump or a something like that is going to be less energy intensive than using something like a space heater. So we really try to discourage that kind of thing if you have the option of a heat pump. Now, surprisingly, in my house, I don't have a heat pump. I have a furnace. What is a furnace doing? It's burning gas to produce heating. Once again, very high efficiency. It's, I think, somewhere close to 90% efficiency, but a heat pump would be more efficient. So that's a heat pump for heating. What if we want to cool? What if we want to make a refrigerator? What is the important thing we care about in a refrigerator? Okay, I heard something about cold. The important thing about a refrigerator is how much heat you remove from the cold part of the refrigerator. And so the Q cold for a refrigerator, this is the one that's important. So the coefficient of performance is going to be the one we care about. So for refrigerator, we care about Q cold divided by what we put in. What do we put into a heat pump? Work. So the coefficient of performance for a refrigerator is the Q cold over the work, while the coefficient of performance for a heat pump is the Q hot over work. Why are they different? Because we had different things we were trying to do. Now, a heat pump will do both. It takes heat out of something cold and puts it into something hot. Let's think about the second law of thermodynamics. What does the second law of thermodynamics say? Ashley really wants to answer, but she also really wants to eat. It says heat spontaneously flows from where to where? Hot to cold. What is a heat pump doing? It's making heat flow from cold to hot. It's making it go against the second law. And you might start to think, wait, it's violating the second law, isn't it? But it's not. And I'll go through the process of how a heat pump works, specifically in a refrigerator, but it's the same basic process in any heat pump. Different kinds of heat pumps are optimized for different outcomes. And so an air conditioning unit is not going to be your most effective heater. A refrigerator is definitely not your most effective heater. But if you think about this, if you look at the numbers, which is always bigger, Q hot or Q cold? Q hot. So if I have a refrigerator in my dormitory room, that's assuming I was a college student, and it is a hot day, some people say, oh, I'm just going to open up that refrigerator and cool myself down. How many people have done that? No, probably didn't mean it, but she had both hands up. A lot of people do that, and me as a physicist, like my wife's all, oh, it's so hot. Well, honey, you're just heating up the house. Because if you open the refrigerator door, you are removing heat from the house with that T cold. And then if you look at the back of the refrigerator, you're exhausting that T hot right back into your room. But the T hot is a bigger amount, or the Q hot is a much bigger amount of heat. So you open that refrigerator door to cool yourself down, and you're heating up the room. My wife and I argue about fans. When you run a fan, what's the fan doing? It's circulating air. But it's making the air move. If you make the air move, you raise its kinetic energy, which means you raised its temperature. Now, the amount of actual raising of temperature done by fan is really small. But I say, what's the point of having the fan on in a room when there's no one there? All you're doing is increasing the temperature by a really small amount by using a really small amount of money's worth of energy. I don't like using energy for nothing. I don't like heating the house on a hot day. So let's turn it off, even though those are minuscule things. My wife's on. But it cools the room. I feel cooler when I walk in. Why do you feel cooler with the fan on? There are two possible reasons here. Why do you feel cooler with the fan on? Okay, one is it gives you a forced convection. Convection was the transfer of heat through an intermediary. And so you have hot skin, air blows over it, takes away some heat, increases the rate of evaporation, so you have even more cooling. That's good. The other one is it is mixing the air so you don't have hot pockets. You don't have, it's hot by the window because the sun's beating in. You come by that window, it's really hot. You turn on the fan, it takes that hot air away. So when you walk by there, it's a little cooler. Of course, that heat has to go somewhere else, so it doesn't have cold pockets either. But those are the two things why we use fans, why we like them. Okay, here is an example of a heat engine. This is, again, the Carnot cycle. The Carnot cycle, but it's run in reverse. So now you have an isothermal expansion at low temperature, adiabatic compression, and then isothermal contraction at high temperature. It's just reversed. It's still the ideal, not real, but the ideal engine tells you about the best possible coefficient of performance. So the calculations that you make with this are used to help you understand, am I doing well or could I do better? Now, one thing that I put the equations for coefficients of performance, but using our relationship between work and heat, which I guess, I wrote right here. You can substitute for work to get it all in terms of heat. And with the Carnot engine, the heat is proportional to temperature, and so you can basically replace all of the Q's with T's. And so for Carnot efficiency, it's temperature hot over temperature hot minus temperature cold, or temperature cold over temperature hot minus temperature cold. Now let's get to the guts of it. Making a real refrigerator. Your real refrigerator has these pieces. So let's just start right here. We have some fluid that comes to the compressor. When you compress a gas, what happens to the gas? First of all, you compress it. You had to have a pressure and a change in volume that made it so the change in volume was down. So was work done on the system or work done by the system when you compressed it? Just think about it simple. I have a bicycle pump. If I have a bicycle pump and I push down and I don't let any air out, did I do work on the gas or did the gas do work on me when I pushed it down? I did work on it. So energy went into the gas. What happens to the bicycle pump if you put your hand on it and you pump a little bit? What happens to the temperature of the bicycle pump when you pump on it? It heats up because when you do work on it, more energy, hence higher temperature. So that compressor increases the temperature. So I had cold gas coming to the compressor, the bluest indicate cold, and out of the compressor comes hot gas because work has been done on it. This here, the condenser, is outside of the refrigerator. And that condenser has a bunch, the tube is going like this. And so you have a lot of surface area on the tube. It's out in air. In fact, you might have a fan that's blowing air over it. If I have air blowing over a hot pipe, what's going to happen? Let's say I have air that's at 20 degrees Celsius and I have a pipe that's at 70 degrees Celsius. Go ahead, Erika. Okay, you're going to have heat that goes from the hotter pipe to the cooler air, and then convection is going to take it away. So is that in agreement or disagreement with the second law of thermodynamics? That's an agreement. That works the way second law says it should be. The hot pipe had heat spontaneous flow into the cooler environment. And so we have heat leaving, and so that's the Q high leaving, and that obeys the second law of thermodynamics. So after going through this long maze, the reason you have a thin pipe with a long maze of it is so you have a lot of surface area, so you can have a lot of cooling, so you end up with basically room temperature gas still at high pressure, but because it's gone through those cooling coils, it's cooled down, that comes to the expansion valve. Now the expansion, this is something, again, you may have some experience with. How many people have used an aerosol can? Okay, most of us have. If you sit there and hold it down for 5 seconds, what happens to the temperature of the can? It's cold. Why? We now have enough physics to answer this question. What happened to the gas when you let it come out? It expands. It's exactly the same as the expansion valve right there. Because it expanded, it was doing work on the environment. Doing work in the environment means energy was flowing out of the gas into the environment. So the internal energy of the gas goes down, and what does that mean for the temperature? It cools. So that expansion then allows the gas to cool. So now you have cold on this side. That's really cold. And then it goes through the evaporator, which is essentially the same thing as the condenser, but it's inside the refrigerator, where you have the air temperature in the refrigerator, which might be, 34 degrees Celsius, and you have this coil that's at, let's say, minus 5 degrees Celsius. How's heat going to flow naturally? From hotter to colder, so it's going to go from the 35 degree air into the minus 5 degree coil. And so that drew heat out of the refrigerator. Once again, that was in complete agreement with the second law of thermodynamics. So we didn't violate the second law of thermodynamics on either side of the heat pump. But the net result, because of the work we did, right? We did work with the compressor. Because of that work, we were able to make the net result have heat flow from cold to hot. So that is how it works. Any questions about how a heat pump works? For the final exam, you'll probably have a question about a heat pump. What would the question have? Well, you should be able to calculate the coefficient of performance. That is, you have, the work and the QH, or the work and the QC, or the QH and the QC, any one of those three variable sets. And you should be able to calculate the coefficient of performance. And of course, you should be able to calculate the coefficient of performance if it's heating or if it's cooling. So you have to be able to think about it, is this being used in a heating aspect or a cooling aspect? And use the correct equation depending on which way it's being used. Because the same heat pump could be used for either purpose. Question, Edika.
So for the final, is it going to be similar to like how we have it?
It will be exactly the same format with the same number of questions, the whole 9 yards. And the same amount of time, of course. I say of course because everybody knows you have a 2-hour final for every class. So you should be able to calculate those coefficients of performance. And of course, you have the same rules about a Carnot cycle, the same rules about energy in and energy out. So there's really not much new here except for you're running a heat engine backward. Make sure you understand what the heat pump is, how it works. Now we're going to talk about entropy. And after talking about entropy, we will have our first clicker question. So entropy. Most everyone has the definition that entropy is the amount of disorder in the system. And while it's an accurate statement, it's a misleading statement. This picture, the two pictures there on the right, illustrates physically what entropy means. The picture A, it says likely, we have the molecules spread out roughly evenly spaced with varying speeds. The unlikely, highly unlikely, has them all in the corner. We can take that, apply it to this classroom. The likely scenario is we all have air to breathe. The unlikely scenario is all the air is in one corner of the classroom and we suffocate. You'd all agree it's more likely that we can all breathe, less likely that we all suffocate. Agree? Just from our natural experience that we've never seen a situation where people were in a room that had air in there, but they all suffocated. According to physics definitions, the likely one has a higher entropy, a higher disorder, as you would say. How did they come up with that? We do statistics. We calculate how many different ways can we have the air uniformly distributed through the classroom. So all the different positions each molecule can have, all the different momenta each molecule can have. We calculate how many different ways that can occur. And then we say, well, how many ways can we have all molecules in one corner? Now, the space is a much smaller space, so it turns out there's a lot less ways we can have that one occur. And then we say the one that has more ways it can occur is more likely to occur. And we define the entropy based on that. The entropy has as its defining equation, the entropy is the Boltzmann constant times the natural log of the number of microstates in the macrostate. So that there is microstates. And you might say, well, I'm glad you gave me that definition that I don't understand. Wouldn't it be so much more useful if I understood it? Microstates is different ways of arranging the items. So take, for instance, I always do 2 dice. I have 2 dice. I started this before in class, didn't I? No? Okay. 2 dice. What rolls can I get with 2 dice? That is what total number of pips can I get for 2 dice? What's the minimum? 2. What's the maximum? And I have every number in between. 3, 4, 5, 6, 7. So those are all of the outcomes I can get rolling 2 dice. We call this the macro state. Now we have the microstates. So let's say that I have a red die and I have a blue die. You all know die is the singular, dice is plural, right? Just so we don't get confused there. Pips are the spots on a dice, or on a die. I just made the mistake there. So to get 2, what am I going to have showing on each die? I'm going to have 1 and 1. So I have 1 pip here and 1 pip here. So the total number of pips is 2. Now if I go down to the next row, the next macro state, to get 3, name a combination that would get me 3. Okay, 2 and 1. So 1 there and 2 there. Or I could have had it the other way around. 1 and 2. So there are 2 different ways to get the roll 3. So there are 2 microstates in that macro state. 2 different arrangements that give the same outcome. If you keep going, it turns out that these add up to, I'm going to put the microstates here. There are 2, there's 1 of these, 2 of these, 3 of these, 4 of those, 5 of those, 6 ways of getting 7. 5, 4, 3. So if we look at these, the number of microstates in the macro state has a peak for the number 7. Now, if we calculate the entropy of these rolls of the dice, the entropy is Kb times the natural log of the number of microstates. So which of these macrostates has the largest entropy? That's the highest S. Now, if you were to try to apply statistics to dice, you would say the probability of rolling a 7 is 6 out of 36. That's 6 equally probable. All 36 states are equally probable unless you have weighted dice. 6 of them come out to be 7. So it has a 1 in 6 probability. It's the most likely. You try to apply physics and apply the second law of thermodynamics, you would say that if I start with both dice showing 1 pip, I pick them up and I roll them, it's going to have to be closer to 7 than 1. Which makes sense, but it's not necessarily true. But to make it so it's obvious, if I had 3 and 3 showing, and I picked it up and rolled it, the second law of thermodynamics would say, what outcome should I get? What's the only number with a higher entropy than 6? 7. So the second law of thermodynamics would say I should get 7 if I re-roll it. But you know that if you have 6 and you re-roll, it does not guarantee a 7. It doesn't even, somebody might say, well, the second law says greater than or equal. It doesn't guarantee a 6, 7, or 8 either. So is the second law wrong? Not if you go back to what it really fundamentally is. It's a law of statistics. The second law is not an immutable law. It's a law of statistics that says in any natural process, the most likely outcome is the one that's going to occur. It's almost like Occam's razor. When given 2 different ways to explain a system, the one that's simpler is probably correct. That's Occam's razor. The second law of thermodynamics says when you have a thermodynamic process, the most likely outcome is the one that's going to happen. It didn't work for only 2 dice. Why? Because 2 dice gives you a statistically insignificant sampling. It's easy to violate the probability on 2 dice. But if you were to do it with 100 dice, you would find the probability curve becomes a much steeper function with a sharp peak. And if you did it with 10 to the 25th dice, you would find your probability function, if you plot the number of microstates going across the numbers, if you did it with 10 to the 25th dice, it would look like that, with virtually no probability of anything except for that outcome. And so when we're working with molecules in a room, 10 to the 25th or so, this statistical law becomes a very reliable law because the probability of not being at the most probable is virtually 0. So it's a probability law. So if we go back to my picture, I have likely and unlikely, highly unlikely. But is this possible? Yes. Not passable, possible. So the second law of thermodynamics says that can happen, but it's really, really unlikely to happen. Do you understand the second law a little better now? Now I hope that audible answer agreed with the nodding heads. I wasn't sure if it was a yes or no. We have a couple more equations. The change in entropy. If you have an isothermal process, the change in entropy that occurs is just going to be the heat divided by temperature. So if I look at the refrigerator, on the hot side, it's isothermal. The heat is leaving at a constant temperature. On the cold side, it's isothermal. So for the refrigerator, I can calculate change in entropy inside is equal to Q cold over temperature cold. Now, the heat is leaving. So Q cold, if I use Q cold as a magnitude, which is what we've been doing, right? I have to put the minus sign because it's leaving. And if I go on the exit side, change in entropy out is equal to Q hot over temperature hot. Now, according to the second law of thermodynamics, we had one statement that heat always flows from hotter to colder. Now we have another statement of that second law that says every process occurring in nature proceeds in the sense in which the sum of the entropies of all bodies taking part is, the sum of the entropes of all the bodies taking part is going to be greater than or equal than what you started with. So if I come up to my example with the refrigerator, according to the second law, change in entropy out plus the change in entropy in must be greater than or equal to 0. That's another statement of the second law of thermodynamics. So we could go and we could calculate. I'm not going to do the calculation right here because I see that I only have 9 minutes left. But you can show that this is always going to turn out to be true, because even though QH is bigger than QC and TH is bigger than TC, it always turns out mathematically that you have, whoa, I made a mistake. Well, we'll live with it. I just have to cycle through a bunch to get to our clicker question. I know the clicker question is now available on your phone, but I want to talk about this first. Here's another example: ice crystals and water. When I heat the ice crystals up, I put heat into the ice, and they clearly went to a less ordered state. As ice, you have very specific positions for the molecules. As water, they can move all around. That's less ordered. That's higher entropy. So that's an example of an increase in entropy by putting heat in. But we have the opposite case. When it gets cold, we have water that freezes into ice. What happens to the entropy if water freezes into ice? It goes down. Is that a violation of the second law? It's not. I give you the answer. It's a rhetorical question, sorry. It's not, because that heat had to go somewhere else. The heat that you took out of the water had to go somewhere else. And that heat that you took somewhere else is raising the entropy there by a greater amount than you lowered the entropy in the ice. So now our clicker question that has one response so far. Given the Planck statement of the second law of thermodynamics, how is it possible for water to freeze and become ice? 33 or web fizz. James and Edward. Okay, Edward's answer, my bad. James. Don't have it? Okay. So we had 19 responses, and because I messed this up, can you tell me what the answer or what this response numbers were? Or is it not showing your phones? Okay, well, everybody's answer chart started with the change in entropy of the water freezing is small. Oh, no. That's a variation. I feel really silly that I did not do this correctly. It's because, well, you can't tell, but I'm recording this here for showing them a bug, but it's not going to work out because of that. Well, okay, everybody said greater or smaller. I can figure it out from that. So I have to count these manually. We have 1, 2, 3, 4, 5, 6, 7. 7 graders, and all the rest are smaller. So that's 9, 12 smallers. So it was pretty evenly split. So here's a reasonable situation for you to talk to your neighbor and discuss which one is the correct and why. And of course, Brittany, you'll just have to turn around and talk to your friends behind you.
section on freezing it level up.
Right?
Oh, we know.
Okay, go ahead and answer again. Okay, now I'm really going out on a limb. I'm going to try again. Okay, nope, still not working. I was talking to the person for like an hour this morning on trying to fix this problem. Still didn't work. So let's just go straight to Peter.
C, because there's more entropy and the environment freezing the ice compared to the water freezing the ice.
Okay, the change in entropy of water freezing to ice is smaller than the magnitude of change in entropy in the environment that freezes it,
Yes.
because you're exhausting more heat at higher temperature. Even though it's more heat at higher temperature, if you think about more heat at higher temperature, it could be bigger or smaller. Depends on the ratios. But it turns out it always is exactly what you said. It's always going to have a greater increase for that exhaust heat's entropy than the decrease for what's inside. So it did not violate anything having to do with, let's stop that recording now, having to do with the second law of thermodynamics. Now, I only have 3 minutes, so I'm going to have just a very, very brief discussion about simple harmonic oscillation. All of our homework will simply be over heat pumps. Oscillatory motion. Oscillations are anything that repeats. This picture here shows a nice smooth repeating function, a sinusoidal repeating function. And for this class, we will only consider the sinusoidal repeating functions. So you can think of something like, I go to church every Saturday morning. That's oscillatory behavior because it recurs at a fixed interval. But it's not sinusoidal, right? That would be a function that goes like this. That's still oscillatory, but not the kind we're going to consider. The name for that is simple harmonic oscillation. So I'm only going to define simple harmonic oscillation for today. Simple harmonic oscillation occurs if and only if you have the net force on an object is equal to, notice there's a minus sign. That minus sign is super important. Some constant times the amount of displacement. That minus sign means that it's a restoring force. It's restoring the displaced object back to its equilibrium position. So for instance, now Brittany's probably not going to like this, but Brittany's head has its position here. If I push it to the side, she applies a restoring force to bring it back to where it was. Right? That's what a restoring force, I told you she didn't like it. Restoring force is a force to bring it back to its equilibrium position. You have to have a restoring force for simple harmonic oscillation. And then the second part, it has to be proportional to how much you displaced it. So if I displace Brittany's head a little, I won't do it, don't worry. If I displace it a little, her force to push it back is small. If I displace it a lot, her force to push it back is much bigger. Where have we seen this? We've seen it in springs. Springs obey Hooke's law. This here is Hooke's law. And so springs, a mass hanging on a spring, is a classic example of a simple harmonic oscillator. It turns out that almost every force, if you have a small displacement and it's an equilibrium, a stable equilibrium, can be modeled as being linear and thus a simple harmonic oscillator. That's why we focus on almost every system that is in equilibrium, a stable equilibrium, can be treated as a simple harmonic oscillator if you have small enough amplitude. Okay, end of class.